Welcome to Measuring the Immeasurable. Today we're going to be talking about using scale to measure area. This is Crater Lake. It's in the state of Oregon. Once upon a time it was a big volcano, but the volcano collapsed, and so over the ensuing hundreds of years, the caldera, the pit of the volcano, has filled with water. So what if you wanted to actually measure how much surface area was covered by this volcanic lake? How would you do it? Well, one of the things that you could do is you could fly over the top of it and get sort of a top-down view of what Crater Lake looks like. If we ignored all of the mountainous terrain and just focused on the lake, we'd have this picture right here. Well, in keeping with the themes of what we've been doing in the other days, we could measure the area of this small-scale object and then scale it up. And so that's what we want to investigate today, is how we would do both of those things. Let's first talk about the scaling bit. Remember that figures are similar if they have the same shape, but not necessarily the same size. We've seen that corresponding lengths scale between similar figures by multiplication, but that the corresponding angles remain unchanged. That was how we were able to measure heights yesterday. But what about the areas of similar shapes? Do they scale by the scaling factor? Do they stay unchanged? Well, let's say we had a perfect square that was 1 unit by 1 unit, so its area would be 1 square unit. Now here's a square that's been scaled up by a factor of 2. What's its area going to be? If I subdivide those 2 units in half, and then mark some grids to help me out, I see that this shape consists of 4 of the 1 unit squares, and so it has an area of 4 square units. So when I had 1 square unit of area at the beginning and I scaled it by 2, the result was 4 square units of area. What if we made a bigger shape? Say one that's 3 units wide. Well, again, I could subdivide the 3 units into 1 unit increments, then subdivide the square, and I'll see that I'll get 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 square units of area. So if I scaled the original shape by a 3, then the area was scaled by a 9. So if we put these things together, we find that if the lengths scale by a factor of s, then the areas scale by s squared. So that means if we can work out the area of a small-scale object, we find the scaling factor for the large-scale object, and then multiply by that scaling factor squared. Let's turn this into a process for measuring areas. We can find the area of any region using a map, a calculator, a measuring tool, and the scaling factor idea. First, use the map scale to determine the scaling factor. Then measure the area of the shape on the map, using some kind of a measuring technique. We'll talk about 3 techniques: the grid method, the mid-ordinate approximation, and a planimeter reading. Once you've got the small scale area, then multiply by the square of the scaling factor to find the region's area. So how do you measure a map area when it's not something like a square or a triangle? How do you find the area of an irregular shape? Well, we're going to talk about 3 methods. The first is called the grid method. And in the grid method, we draw a square over the region, and we count up the number of squares the region takes up. So essentially, we put graph paper down on the shape. We'll mark those squares that the region sort of overlaps, and then count up just the number of squares we've marked. So in this case, we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 65. And so since these were the squares that covered the region we were looking for, that tells me that the region was approximately 65 square centimeters in area. I mean, that's about as easy as we could hope for right here. But when there's a lot of squares, it takes a long time to do. Fortunately, we can do a similar thing with less counting. It's called the mid-ordinate method. And the basic idea goes like this. Draw a line that cuts through the middle of the shape and mark off even intervals on it. Let's say 1 centimeter intervals so that it would match what we did last time. Now, in between each one of those tick marks, you're going to draw a line perpendicular to the line you just drew that goes up and down through the shape. That word in between the tick marks is sometimes called the mid-ordinate mark, which is where the technique gets its name. Now what we're going to do is we're going to measure the lengths of each one of these orange shapes that we just drew. So the first one is 2.4 centimeters, then 5.6 centimeters, then 5.6 centimeters. The idea here is we're measuring how many of the little blocks we could have stacked on each one of these lines without actually having to stack the blocks on it, without having to count the grids on it. We're implicitly approximating the shape's region by a bunch of little squares and rectangles like we did before. We just don't have the graph paper. So instead of trying to find the area of this shape, what we're thinking of doing is we're really thinking of trying to find the area of this shape instead. Now the area of a shape like this, well, since it's built out of rectangles, we just add up the areas of all of the rectangles. Length times width, length times width, length times width, add them all up. Notice that in this algebraic formula, all of the widths of the rectangles are the same, so we could factor it out and just get that the area is approximately length 1 plus length 2 plus length 3 plus length 4 plus, adding up all of the lengths and then multiplying by w. So let's go and do that. On this example, we'll take all of our lengths, 2.4, 5.6, 5.6, up to 2.6, and add them up, we'll get 62.5. So that's the total length of all of the mid-ordinate marks we made. Then we'll multiply that by the width of each one of the shapes, which was 1 centimeter, and we get 62.5. So we've approximated the shape by rectangles whose areas total to 62.5 centimeters. And that's pretty consistent with what we had before, which was 65. So to summarize the technique, draw a line across the region. Then draw perpendicular lines cutting it of even width. Then the area of the shape is approximately the total length of all of the lines you drew going up, multiplied by the width between the lines. The idea of computing an irregular area by approximating the shape with squares or rectangles is sometimes called Riemann sum, and with a little skill it can be used to compute the exact area of a shape. Unfortunately for us, this process is called integration, and it needs calculus, which is a little bit beyond what we've got today. However, there are special mechanical tools who can do this job for us, and they're called planimeters. A planimeter is a mechanical device for measuring a region's area by tracing around its perimeter. On a standard two-armed planimeter like this one right here, it has a heavy base to keep it from moving, two arms that allow it to move and rotate around, a tracking window that lets you see the perimeter of the shape, and then a reading display that we can use to compute the area. Now the reading display is kind of technical on a planimeter, and so I want to show you what it looks like and how you read from it. So the display will look something like this. It measures values in square inches using two different spinning wheels. The first thing is this pinwheel which spins around, and that gives the tens digit of an area. In this picture, the pinwheel is between 2 and 3, and so we'll read it as the smaller of those numbers, 2. The other spinning wheel is this dial over here. It gives the ones and tenths display. In this case, the spinning wheel is calibrated between a 5.4 and a 5.5, and so we take the smaller number and we get 5.4. So that means that this display is reading the number 25.4. 2 in the tens, 5 in the ones, 4 in the tenths. So how do you use a planimeter to measure area? Well, let me make a simple picture first, and then bring back the area we were looking at. So how you use a planimeter is pretty straightforward, actually. You start off by taking an initial reading on it. So say you look at the planimeter reading display and it says 25.6. So you write that down. And you also mark a starting spot on the shape's perimeter. So then bring the planimeter arm over to it, and then slowly trace around the perimeter once, clockwise. So you move the arm around, keeping the perimeter right in that little tracing site. And when you've gone around one full time, you stop. Read the display a second time. It will have advanced. It'll be a bigger number than it was before. So in this case, say the planimeter reads 35.4. Take your final reading and subtract the initial reading. In this case, we get 9.8. And that's the area in square inches. Couldn't be simpler with a planimeter. Of course, 9.8 seems a lot different than the 62.5 and the 65 we've got previously, but remember those values were in square centimeters. And so this would be a good time to remind us about how we scale units. To scale between the units, 1 inch is equal to 2.54 centimeters, so we can treat this as a scaling factor. The scaling factor would be, well, we'll take the centimeters, what we're shooting for, divided by the units we have, inches. And so we're going to get a scaling factor of 2.54 centimeters per inch. And then to scale up areas, we multiply by the square of the scaling factor. So we'll take 9.8 inches, what we measured on our small scale. We'll multiply by the scaling factor 2.54 squared, and that comes out to being 63.2 centimeters, which is very consistent with the other results. Now, a two-armed mechanical planimeter like mine can cost upwards of $200. They're not cheap. However, you can make a one-armed planimeter with some basic tools. It won't be nearly as accurate, but it still does a pretty good job. So the tools you'll need are a ruler, a protractor, some tape, a paper clip, some washers, and a couple of binder clips. So here's what you do. Take your ruler and your protractor. Put the protractor on one end of the ruler and tape it to secure it to the side. Then take your paper clip and unfold it so that you have a pointer end on one side, and tape that to the front of your ruler. Next, take out those binder clips and clip both the pointy edge and the back protractor to them. This adds extra stability, and on the front end where the paper clip is, it's going to give you a helpful handle for using this machine. Finally, take those washers and sort of stick them inside the binder clip to add additional weight to the back end. This always works better the heavier that back end is. So this kind of a device is sometimes called a hatchet planimeter, because I suppose if you turn your head sideways and squint, it kind of looks like a hatchet. In keeping with that name, though, the back side of it is called the blade, whereas the front side is called the tracer. And so how it works is pretty similar to the other one. Take your shape, take a starting point on the shape, and then place your hatchet planimeter so that the pointy end is on the shape and that the blade rests somewhere off on the side. And mark where that is. That's your initial reading. Now you're going to do exactly what we did before here. You're going to go and trace around this shape once, clockwise, holding on to just the binder clips at the very, very top. It's really important that when you trace with a hatchet planimeter that you don't hold the middle of the ruler and that you don't sort of bonk it. You have to just hold the front end at the binder clips and just hold it gently enough so that the top end makes contact with the paper, but that you don't twist it or torque it on your own. So go around the shape once clockwise. When you get back to the top, the blade will have moved to a different spot. And so you're going to mark where the blade has ended up. That's essentially your second position, your second reading. So how do you get area from this? Well, you're going to measure these two distances. The distance from the point on the perimeter to the initial reading, and the difference between the initial reading and the final reading. Take those two lengths and multiply them, and you have approximately the area of the shape. With a good, heavy hatchet planimeter, this is usually a pretty accurate approximation. With a handmade one like ours, you can have a lot of user error. So my suggestion is it's best to make two measurements from two different starting points, and then average your results together. So now it's your turn. Split up into two-person teams and work on the measuring irregular worksheets together. And at the very, very end of it, hopefully, you'll be able to figure out the question we first posed. Just how much space, how much surface area is covered by Crater Lake?